So I want to focus on that middle section, the planning. When we look at a proof problem, how do we create a plan for ourselves? And I just kind of want to impress on you guys that there's not really like a set of steps that I can give you that really show you how to create that middle section of your proof. We're really going to have to kind of come up with some ideas and tinker around until we come up with something that makes sense and gets us from our initial hypothesis down to the conclusion. So in this proof, what we can assume is our hypothesis here. That's going to be our given. So we can assume that M is the midpoint of AB. And that is just a given for us. It is our hypothesis. And where we're trying to get to is this equation. We're trying to say that AB, the whole thing, is equal to 2 times AM. That's what this equation is saying. This is the conclusion that we are trying to reach. So that will be our last step. I'll even fill it in there. So AB equals 2 AM. We know that's where our proof needs to end. I said I kind of want to focus on the planning. So what I'm going to do, I'm going to write some ideas that we can look at and see if they get us anywhere. The first thing that I notice is our conclusion involves an equation. So at some point here, I don't start with an equation, but I need to end with one. At some point, I need to introduce an equation that involves both AB and AM. Since we're dealing with a segment here, we could use the segment addition postulate. So just using the segment addition postulate for this would give us an equation like this. Again, this is my plan. I'm going to go ahead and probably erase all this stuff in the middle to finish my proof. But using the segment addition postulate, I know that AB, the whole thing, is equal to AM plus MB. And not DMB. That is using the segment addition postulate. Anytime we have a segment like this that's cut up into 2 smaller pieces, we can use the segment addition postulate to create an equation for ourselves. So that introduces an equation that has these 2 segment names in them. We have AB and we have AM. The thing we're missing here is well, not really missing, but the thing that is important that we're not talking about is we don't actually want MB in our equation, in our final equation. So in some way, we need to be able to get rid of this. We need to do something that would actually get rid of this. And the only other thing that I know that I haven't really used is our hypothesis. I haven't made use of what our hypothesis is trying to tell us yet. If M is the midpoint of AB, well, when you have a midpoint, that means that you have divided your segment into 2 equal pieces. So based on that, I know that AM and MB are actually equal to one another. That's because of the definition of what a midpoint is. So the definition of midpoint. Again, when you have a midpoint, the 2 halves are equal to each other. That is the definition of what a midpoint tells us. And now, keeping in mind our goal, remember our goal was to write this particular equation right here. AB is equal to 2AM. I have this equal relationship. This relationship allows me to make a substitution. Anywhere that I have AM or MB, I could replace it with the other one. So that's going to let us actually get rid of MB altogether. I can take AM and put it where the MB was using the substitution property of equality. Because these things are equal, they can be replaced with one another anywhere we want, really. So that would turn this equation right here into AB equals AM plus AM. And that was achieved, again, by using the substitution property. Substitution property of equality. Again, anytime two things are equal, you can make a substitution for one of those things, which we did. And again, I know that this is kind of the way I need to go, but really I'm just seeing what I can do with all the different relationships here, using segment addition postulate, using midpoint, all that stuff. To go from this equation to what we want, we're basically there, right? I have on this side, I have AM plus AM. If I add those together, if I just simplify that, right? These are like terms, I can put them together. I just end up with 2AM. Just like if this was X plus X, I'd end up with 2X. So I can actually just add those together. I can just use a little bit of simplification. I can simplify this and result in what we wanted. AB is equal to 2AM. So actually my plan here has kind of turned into the proof. What I was thinking about and what I was kind of writing down turned into a proof that we can use for this particular problem. Just need to draw a couple lines in here and write some step numbers and I'm good to go. Oops. Now, it's not always, sometimes we might need to write a plan down beside it and it might not go anywhere and we'll have to make adjustments to it. But in this case, just kind of talking through it, seeing what we could do with the segment addition postulate and the definition of midpoint, led us down to a proof that got us exactly where we needed to go. Okay, so this is one type of proof that's going to be pretty common for us. It's going to involve writing an equation that involves our two elements that are in the conclusion, or writing some sort of relationship between them, and then changing that relationship, manipulating it in some way based on our other information until it says what we want. That's going to be one type of proof that we'll do a lot. We'll start with a single equation and we'll kind of change that equation until it reflects whatever our conclusion was supposed to be. I mean, obviously we can't just change it randomly. We have to change it based on facts, based on things we know, but change it into our conclusion. So this is one common type of proof that we'll have. And it might be with angles or it might be with segments. I'm going to go ahead and clear this and do another example here, where again, we focus on this process and this planning process. I went too far. There we go. Okay. So here we have, this one's a little more complicated, but we have AC, that's this segment right here, is equal to DB. All right, I can see the markings on the picture that help me say that. The other thing that we have with this proof is it says, our conclusion says, we are trying to show that AD, so that goes from A over to D, so this whole segment right here is equal to CB. So that would be this segment right here. All right. So this proof is going to be a little different than the last one. I know that already because, well, I've done it, but in this case, I don't really see a way, unlike the last one, I don't really see a way we can write an equation that has both AD and CB in it at the same time. I don't see any relationship that directly links AD to CB. So I'm going to have a hard time coming up with an equation that actually has those together. But that's not going to stop us. Let's write down the beginning part here, just to kind of get that in place. So that's our given. That's our hypothesis, right? And this is our conclusion. So our hypothesis given, our conclusion is what we're trying to get to. Instead of writing one equation, now this is another type of problem. I'm going to write my plan here. I'm probably going to erase this and kind of reorganize it. But here's my plan. I can write two separate equations, one for AD and one for CB. And I'm going to do that using the segment addition postulate. So let's see what those equations look like. So AD would be equal to, so AD, that's the top one here, AC plus CD. So that's AC plus CD. And the other equation, another equation for CB, so CB is this one, is CD plus DB. And so that both of those are just using the segment addition postulate. Okay, now, in some way, I need to be able to put these two equations together because these are the only equations that I could really write that involve these particular segments. At least off of the top of my head there, those are the only ones that I could do. So what I see here is, I notice they both have some things in common. They both have this segment as part of the equation. And the other thing I notice is actually that these two things, both of those facts are involved up here in my given information. I actually know those two things that I circled are equal based on my given information. So what that actually tells me, remember when two things are equal, is that I can make a substitution. I could replace either AC with DB or DB with AC, whichever way I want to do it, or both if I wanted to. In this case, what I'm going to do is I'm only going to replace one of them. I'm going to get rid of this AC. And in its place, I'm going to put DB. So in its place, I'm going to put DB. Now, now I have these two equations, and I hope you notice that I'm going to rewrite them, but I hope you notice that the right sides of these equations are actually the same. Not identical, but equivalent. They both have DB plus CD or CD plus DB. Those two expressions there on the right sides of our equation are actually the exact same thing. Since they're the same thing, that means that these two would have to be equal. Since AD equals this and CB equals the same thing, the transitive property would have us be able to say that these two things actually have to be equal by the transitive property of equality. Anytime two things equal the same thing, then they would have to be equal to each other. Again, that's the transitive property. It's a little bit of a complicated idea, but it's something that we'll use a lot. All right. This is sort of basically a proof. We haven't quite got everything in there, but this is kind of a proof. There's a little bit of extra stuff, but I'm going to delete some of this here and kind of fill it back in. This was AC plus CD. So remember, a proof having that two-column structure, we set up two equations using the segment addition postulate. So this was step 2. Then right here, remember what we did was we made a substitution. We replaced AC with DB. So that was the substitution property of equality. And then finally, using the transitive property, we were able to arrive at the conclusion that we were going for there. So this is actually now a proof. This is kind of not the only other kind of proof, but another common type of proof that we'll have to do, where we set up two separate equations and then show that those two equations can be put together using the transitive property or using substitution. And so these are kind of two major types of proofs that we'll be doing. The last one where we had one equation and we manipulated it to arrive at our conclusion, or on this one where we wrote two equations, and then by working with those two equations, we were able to say, okay, these two equations can actually be put together into a single one using the transitive property, and that is our conclusion. So this is a common type of proof that we will also be doing. Again, I'm not expecting us to be able to do these on our own yet, but right now this is kind of understanding what happened here is kind of where I hope we can get to. All right, let's move on. One more proof that we can do. All right, this one here is going to be somewhat similar to what we just did. So I'm going to show how we can do this one. Give myself some lines. All right, so we have angle 1 and angle 2 are supplementary. That's our first given. And angle 2 and angle 3 are supplementary. So these are both given to us. So angle 1 and angle 2, angle 2 and angle 3 are supplementary. And again, that's given to us. That's what we always start with. Now, our goal at the end of this proof is going to be to reach our conclusion that angle 1 is congruent to angle 3. Kind of setting up the outline of the proof. It's this middle section that we need to figure out here. So doing that, supplementary is a really nice relationship. It actually lets us write an equation, right? Whenever we know that two angles are supplementary, we know they actually have to add up to 180. So these two relationships will actually let me set up two equations. The reason that I'm not able to set up a single equation is because I can't actually write, based on this, I don't have a direct relationship between angle 1 and 3 yet. And remember, that's what we're trying to establish. So I can't just write one equation, but I can write two. And that's based on this statement right here. So I can say that the measure of angle 1 plus the measure of angle 2 has to equal 180. And also the measure of angle 2 plus the measure of angle 3 has to equal 180. And that's just the definition of what supplementary angles are, right? Since we know they're supplementary, this is the definition of supplementary angles. Easy enough. And this one is actually even easier than the last one. Since both of these two relationships equal 180, then I can set these two sides equal to each other by the transitive property. I can say measure of angle 1 plus measure of angle 2 would have to equal the measure of angle 2 plus the measure of angle 3, since they both equal 180. And that's using the transitive property. So we're able to take our two equations, put them together into one equation, and conveniently, we can change this equation so that we actually end up with just angle 1 and angle 3. I can actually just subtract the measure of angle 2 from both sides. If I subtract the measure of angle 2 from both sides, that leaves me with the measure of angle 1 is equal to the measure of angle 3. And all we did was subtract on both sides. So that's the subtraction property. Subtract the same thing on both sides. Subtraction property of equality. And now, this is one of those situations where technically, this is kind of the same thing as what we're trying to prove. Right here, this statement says that the measurement of these two angles are equal. It's almost the same thing, but in a formal proof, you would take an additional step. Since the measurements are equal, that means that you can say that they are congruent. That's what it means to be congruent. So we say this is the definition of congruent angles. Since their measurements were equal, we're allowed to say that they are congruent to one another. So this proof was pretty similar to the one that we just did before. We couldn't write a single equation that related angle 1 and 3, but we could write two equations and then put those together using the transitive property. Now, technically, that's the transitive property of equality. So I'll add that in there. Now, again, I'm not expecting that you are able to create a proof like this right now. The homework problems that I assigned you don't have you actually create a whole proof from scratch. They have you kind of fill in the blanks on proofs or take a plan that's already constructed for you and turn that into a proof. So kind of the harder parts, at least in terms of connecting things, are already done, and you're just kind of filling in the rest of the stuff. So hopefully that's a little bit easier. So I want to talk about the homework. Tomorrow we'll actually go over a few of the problems just to kind of make sure everybody understands what's going on. So let me leave this.